across the board for all of transportation. The highway portion of it, when it comes to the things that you guys are most interested in, the first year for FY 2016, there's a 5.7% increase. And then for every year after that, there's only a 2% increase. So that's not as nice as what we would have hoped as an agency. Actually, our agencies promoted regulations before the FAST Act was put into law, as we were pushing for closer to like a 30% increase. So, but we have a long-term bill, and we do have some increased funding. The other challenge is within the programs that we work specifically for research, development, technology deployment, and innovation are overprescribed with some new grant programs for freight congestion management, as well as some innovative ways of generating revenue to the Highway Trust Fund to maintain its solvency. So our discretionary portion, the part that's not spelled out in the law, is down nearly 25% for us in the program. So we're still going through all the provisions and all the regulations, the multiple thousands of pages to have a better understanding and how we're going to deploy our program moving forward. But we're all very happy that now we have at least a long-term fund. And this is just those highway authorizations projected for the next 5 years. Of course, these are also subject to annual budgetary appropriations. So each year will actually tell us whether or not we'll actually get the full amount that they have in the law or not. So with that, I'm going to transition to more of the technical things. Many of you know that we've got a couple of these expert task group meetings. They're really open meetings with the goal of having everybody within the industry and the community talk about technical issues. Anybody can attend those, and we encourage as much attendance as we can. It's very much an open dialogue, and you get to see the good and the bad and the ugly with everything that we do within the industry here as well. Our last meeting was last September in Oklahoma City. John Bukowski, that many of you know, he's our team leader in our office. He manages the mix and construction ETG. I manage the asphalt binder ETG now. So I'm going to be touching a little bit on both of the outcomes of those two meetings there in September. We also have a sustainability pavements technical working group, and that's in a kind of a hiatus right now as we work through the FAST Act program to see how that has impacted the sustainability program. So, but Gina Ahlstrom in our office as well manages the sustainability part, pavement sustainability. Let's see. Also, we've entered as part of, we've got multiple contracts across the U.S. with technical entities, primarily through the National Asphalt Pavement Association, as well as the National Center for Asphalt Technology, as well as the Asphalt Institute. We've entered part of our co-op agreement with NAPA is to be able to host our presentations and meeting minutes, so now those are available at the asphaltetgs.org website for everybody to download. We've only got the last couple of meetings populated right now, but our goal is to work backwards and try and get more of our past meetings loaded up for everybody as well. But you can go there and directly download the meetings, all the presentations, and the minutes as well. Here's just a snapshot of the things that I'm going to mention. I'm going to try and be very quick. As usual, I have too many slides, but I wanted to make sure that you had access to those slides in the presentation after the meeting as part of the meeting minutes, if you will. So if I don't spend a lot of time on any one slide, at least you'll be able to go back and reference it as well. I'm gonna start by looking at cracking, and you might say, well, what's cracking have to do with modified asphalt? But I think most of you know that has a significant impact on that performance. And some of our initiatives on the mixture side involves all the activity within the industry on trying to either develop or surround and narrow into one or a series of 1 or 2 or 3 cracking procedures that we can really rally around in advance. So there's 4 basic cracking modes that are being discussed right now: low temperature, reflection, bottom up, and top down. They all have different mechanisms, and they all have somewhat different tests now being targeted to address those. The 2 basic loading modes that are being discussed right now are the monotonic or single loading and the cyclic loading. I think the majority of people understand that cyclic loading really represents more of what the materials see, but you also have time constraints and other things. So there are some people that are looking also at the much simplified monotonic tests in order to evaluate cracking performance as well. If you look at the broad range of the different tests, and I'm going to show another slide that includes what they are by name and the standards associated with them, you can see that there's a broad range of different strain conditions as well as number of loads from that single one monotonic load to the cyclic or repeated loading. And they all have different mechanisms that are associated with those. We all know that in reality, our pavements experience multiple load cycles, multiple load magnitudes, multiple strains, multiple temperatures. And so the struggle with the industry is how do we manage to try and capture the performance of our materials across those multiples, but also make it to where it's not onerous or something that most people can't do in their own laboratory. Here's the 10 protocols that have been highlighted as part of a national research effort. These are all being discussed and which ones want to be advanced on a national level. Individually, states are grabbing or using some of these tests already and are advancing standards with some of these tests. And you can see the broad range again from more simple monotonic type tests, such as the semicircular bend, all the way up to the one that I'm primarily going to talk about that we feel like gives you the most information is running the cyclic fatigue with the asphalt mixture performance tester, the AMP. This is just a snapshot of all the standards that are available for these tests. Some of them are standardized within ASTM and AASHTO. Others have state or university issued standards. Some of them are still in research and development. Some of the standards are still in provisional status and are working through improvements with the standards bodies and their technical communities as well. I'm again going to focus on the asphalt mixture performance test because we put a lot of money and effort into the support of this equipment as well as the strengths of the information that comes out of it. We've got a lot of standards in place already, provisional standards that run the gamut of looking at the real mechanistic material properties of the mixtures under similar conditions as what they would experience on the highway. And the most recent one is the one you see there on the bottom, the TP107 test provisional for the cyclic fatigue protocol. On top of the dynamic modulus E-star test for stiffness, which is a direct input into the pavement ME design software, which Dr. Hall is going to talk about later on today. We also have flow number testing for rutting. And now we've got the companion cyclic fatigue testing protocols as well, which in my opinion aren't that complex. The analysis methodology is complex, but I only have to hit a button on a computer to do that. I relate it a little bit to like a DSR. Binders are very complex. The DSR equipment does some very complex things in testing the material. The analysis is very complex, but we have technicians that can manage to run that equipment, run those tests, and give us very meaningful data in order to characterize our materials. And so this is a similar circumstance here with the cyclic fatigue. So why are we looking at it? So I tried to get a top 10 test, but I failed because I only got to 9. Really, it really comes down to the strength of the test and the information it gives you from your materials, but there's also a very strong history and pedigree that starts with the aerospace industry. There's been a lot of work to get us to this point from not only within our industry, but outside of our industry, looking at material fracture mechanics, and then to really get to where we have a very simple piece of equipment that's readily available to the community to use as well. And again, the standardization part, which is important to make sure everybody's doing the same things. If you'll let me divert a little bit on the background, I think this is a little bit from the standpoint of understanding, again, why we're coming this way. If you read this description of the problem, and I'm not going to read it word for word, I'll let you digest it, and we've redacted some of it for you to kind of consider here. And you'll probably guess that this isn't necessarily from our industry and our community, but as you read it, it really does kind of sound a lot like asphalt, doesn't it? But if I remove the redactions, really what we're talking about is we're talking about rocket science. And so you say, well, wait a minute. You know, rocket science, materials, how does this all play together? Well, I don't want to make you believe that I'm up here and I know what a rocket scientist does or that I can design those things. But I can tell you that the methodologies for evaluating materials that are being developed to characterize our materials now have a solid foundation in rocket science and solid propellants. And I think that there's a tremendous strength there with regards to characterizing materials and modeling them as well. So initial solid rocket propellant was primarily asphalt or rubber and mixtures of other things. And so there's a long history on this going back, many, many decades. That's no surprise. There's lots of information out there. For the sake of time, I'm not going to dwell on a lot of them, but I want to get to a point, is that now we've got very large applications of solid rocket propellants. And there's something that's very critical to these when it comes from mission safety or protocol, and that's fracture of the solid rocket propellant within the booster rocket. That's a very dangerous thing, and it leads to things exploding, uncontrolled burns. So they've spent a lot of time to make sure they understand fracture mechanics in these materials, which primarily are a mastic, similar of asphalt and other materials, similar to what we deal with in our pavements right now. So why is that important with the burn rates? There's a lot of different shapes of these solid rocket propellants to try and control burn, how quickly they burn, the burn shape, the burn pattern, how much thrust they get, how long this thrust is maintained. But one of the things is they've got a very narrow window of temperatures that they operate with maximum efficiency. And again, if they're outside of that range, then they tend to have cracks or fractures within that propellant. And if they're left undetected, which it's very hard to detect when they are in that total fabricated state in a rocket, things go incredibly wrong. I do have a brief video here that I think is I love these old videos, so some of it is a little bit for entertainment value. But John, if you could slide forward, I think, to about 8 minutes, 30 seconds. This gives a better idea of understanding what I'm talking about for the basis. Yeah, right about there.
Primer to set off a larger charge of powder,
which
in turn ignites the propellant charge. From this point on, the action is just as we've already explained. The high-pressure gases created by the burning propellant, accelerated by the nozzle, act to give the motor thrust. All rocket motors carry both oxidizer and fuel. Both are mixed together in solid propellant grains in such a way that they will remain inert until they're ignited. Fuels most commonly used are asphalt and oil, rubber, or rosin. Oxidizers are usually potassium perchlorate, ammonium perchlorate, sodium, or potassium nitrate. There are some compounds which furnish both fuel and oxidizer, such as nitroglycerin, nitrocellulose, or ammonium picrate. Propellants of this type must be mixed with inhibiting materials so that they will burn rather than detonate. The regular fuel and oxidizer mixtures are frequently restricted too, but only after they've been mixed and molded according to the design purpose of the rockets for which they're intended, when certain surfaces are coated to control burning. These are called restricted burning charges. There are many more shapes, but these three are good examples. They are the star-chambered, the cruciform, and the solid cylindrical. The star-chambered grain has a star-shaped passage running through the length of the charge. It is restricted on the outer surface where it comes in contact with the chamber walls. This design was developed to provide a constant burning area and reduce combustion chamber wall temperature. The cruciform is restricted on two opposite sides of the crossform and each end, leaving a large burning area which will remain constant throughout the burning period. The solid cylindrical grain is ignited at the nozzle end and is usually coated so as to restrict burning on all surfaces except the nozzle end, and thus has earned the name cigarette burning. Multiple grain and the hollow cylindrical are almost invariably unrestricted and burn on all surfaces simultaneously. Even though most solid propellants will store for short periods, under extreme climatic conditions, such temperature variations will have a definite effect on their amount of thrust and the length of time they will burn. Propellants which are heated before igniting will burn rapidly, giving greater thrust, but shortening the total burning time. Coal propellants, on the other hand, will burn more slowly, giving less thrust, but will burn appreciably longer. Neither of these conditions are liable to create any hazard as long as temperatures are within design limits. However, there is one exception. Propellant grains become brittle in extreme cold and can be fractured if handled carelessly. The danger is that since the propellants are inside the combustion chamber, such a fracture would not be discovered. If this were to happen, when combustion reached the fracture, too large a burning area would be presented, suddenly increasing pressures beyond design limits, and the rocket would blow out.
And there you go.
Here is a liquid propellant motor of the bipropellant type.
So I appreciate you indulging me on that a little bit, but I think that gives you a good idea as far as why it's important to understand fracture mechanics of these materials. So somebody who is very well known in the modeling of pavement materials and materials in general is Shapery. And so his modeling and applications were used to move forward into solid rocket propellants. And there was things written in journals, dating back to 1976, specifically with the Shapery theory. That's moved onward into work done by Dallas Little at TTI and Dr. Richard Kim, that's at North Carolina State now, to develop the viscoelastic continuum damage model. And that's where usually people's eyes start to glaze over, because you start saying things like continuum damage, and simplified continuum damage. And that's where I always like to refocus people and say that these are complex models, they are complex characterizations, but the tests to run and the inputs for those are really not that complex. And we've got the tools to do that now. This is not a Johnny-come-lately methodology. If you do research on asphalt and continuum damage, or into the database on how many published research findings are on those, you'll see an explosion, hundreds of papers on this subject matter. So it's something that we're very interested in as far as bringing a valuable tool to characterizing the materials. As I mentioned, we've got unified common equipment now. We've got unified common compaction controls, unlike some of the other methodologies, the other fracture tests that are being discussed. We've got the leveraging extended time temperature superposition within that system, so now we don't have to test at many temperatures or as many loading or strain conditions that we would have to with a lot of the other tests, and we can get much more meaningful information, similar to what we do with binders as well. There's much more certainty in that stress-strain state within those cylindrical specimens than beams or other shapes that are being used in some of the other tests as well. But the bottom line is really it tells you a lot about your mix, and it connects that mix design to our construction and our distress prediction and what we're seeing actually in the field. So that's something that we're really excited about. So now we'll get into some other areas, and I'll be quick and brief. We do have a new RAS task force within the expert task group, looking at issues primarily with regards to shingles, because shingle binders are very much different than what we're used to working with. They have different characteristics, much stiffer materials. If they've been sitting on a roof for a long time, then they're very highly oxidized as well. So struggling as an industry how to effectively use these binders and how to address the quality of the materials that use those. Right now, the focus is tending towards the brittleness of that blended binder. There's discussions on what we're calling the delta TC, or critical temperature, determined by your BBR criteria, the stiffness or the S value, and the relaxation critical temperature determined by the M value. This is going to see, you're going to see this come up as a constant theme in a lot of the things that we're doing now to characterize materials, because of a lot of early failures that we're experiencing across the country in the field that aren't always associated with this aging characteristic or this ability to relax over multiple cycles, but it's a contributing factor. So things like recycled engine oil bottoms and other materials that are getting higher usage, we feel like this is going to be a good tool and a simple tool with tests and data that are already available to us in order to try and control that parameter as well. From a worst case scenario, we think this will work because the blended binder, assuming it's 100% blended, I think we can all agree that that's probably not likely the case with RAS binders in actual practice and construction. But with the assumption of fully blended binders, then we're giving a kind of a conservative approach there. There are some pros and cons. I think one of the biggest cons is that it doesn't address the other mixture of volumetric issues associated with the use of shingles, the materials that are contained there aside from just the binder, as well as how do we make sure other materials that are being used within our industry are not inappropriately caught up in the criteria. And that's some work that we need to do as we move forward. And then it also gets complicated when you add that and RAP and you combine all these other things together like we typically do. So right now we're developing some recommended proposals. We've got a lead on that task group and a lot of other people. One of the recommendations, possibly to further simplify it, is to have a recycled binder ratio limit or a conservative limit based on that delta TC criteria. It would likely be lower than what we're seeing in practice now across the country as far as weight or volume of shingles that are being allowed. But if somebody wanted to exceed that value, then we would have additional criteria to do additional test and characterization to make sure we didn't have a negative impact. I quickly want to mention we've got a couple memorandums out we've issued out to our division offices to highlight this issue with our state agency partners because we very much wanted to get ahead of some of the failures we were seeing in the field, and so we've directed them to pay some attention here and work with our state agency and industry partners to make sure it's not an issue within their state and to make the right revisions. We also like to highlight and remind everybody that our long-standing position is that any of these recycled materials should not adversely affect performance, safety, and the environment. So even though they may be environmentally sound and we're always looking to recycle materials, we do have a primary goal of making sure that we've got performance. And so that's one of the driving factors here in the recommendations. MSCR activities are ongoing. Mike will probably mention that as well. Mike Anderson, when he discussed some of their activities, we work very closely with AI through that cooperative agreement to get information out and listen to our partners. We are really targeting some of the, as more and more of the use and the standardization, regionalization use of this standard is occurring. We really do want your feedback in how those things are working for you to see if there's anything that we need to address or refine moving forward. So please work with us and work with Mike and his group to do that. Ground tire rubber has kind of fallen off a little bit in the urgency as it was just a couple years ago, but we're still doing a lot of work there. I think one of the biggest activities that have come out of that is the standardization or the finalization of the cup and bob geometry that has been primarily driven by work from Anton Parr in cooperation with Caltrans and the universities in California. But this is going to go a long way for us to try and move these materials into our PG grading system. And so we're looking at leveraging all that previous work that was done and moving forward with characterization protocols using the cup and bob geometry. There are, like anything, there are pros or cons. It's a larger volume of material. It's going to take a little bit longer to heat up, get temperature equilibrium, things like that. But I think the pros far outweigh the cons. Re-refined engine oil bottoms. We have a new task force on that item as well, looking at rheological parameters. That one's also focusing, really coming to fruition to focus and move forward with delta TC criteria as well. It fits into the same characterization scheme as far as making sure we have materials that don't age at an accelerated rate and still provide us for that relaxation over multiple environmental schemes and multiple loading schemes as well. There are some consensus items on the delta TC, and there's some other guidance within the industry and within the Asphalt Institute and their technical committees that will be coming out soon, moving us more in this direction as well. So we think that that's going to be one of the primary tools that we use to evaluate these materials moving forward, to characterize how they perform and to establish some sort of use limits or guidance. And then as I start to wrap things up, one important things that will affect you guys as producers is we're revising the LTP bind software with some significant improvements as far as the weather data. And we're looking for volunteers, but we're tapping into NASA climatic data. That's real-time data, a very advanced amount of data. So we're leveraging that, and it also gives us, instead of relying on dedicated land-based climate systems that have equipment, is that we can basically lay out this satellite-based system in a grid pattern across the United States, and we can get information from down to very small distances, down to about a mile to a half-mile distances, instead of the hundreds of miles of distances between our land-based stations right now. Without getting into details on the mirror data, we are releasing the alpha and beta versions, and we're looking for people to evaluate those. So please contact Larry Weiser if you're interested in looking at that new revision and new release, and give us your feedback. We would very much appreciate that. The final notice is we're starting out a new initiative within the agency this year, targeting 10 states with some dedicated funding for us to pilot some demonstration projects to advance initiatives on increased pavement density. We're looking to get 10 states by the end of this year to take their existing technologies, not require anything new or implement anything new, but then raise the bar and try and achieve 1 or 2% increased density. So the tools we have available for materials, as well as things like intelligent compaction, as well as optimized mix design or balanced mix design, and making sure we have proper effective asphalt content, we feel like this is very easily achievable. So we're going to be piloting that as we move forward. We've generated a lot of data and past historical information on what just a 1% increase in field density means with regards to performance life. And again, I think for us to stay competitive as an industry in the environment that we're in is that this is going to go a long way to help us do that. And then, as always, we're always looking for partners to showcase and evaluate materials. So another part of my program is the Mobile Asphalt Testing Trailer, or the MAT. It's funny how that works out. I know I used my full allotted amount of time, but if there's one quick question, I'll be more than happy to take it. Excellent. You're still waking up. I appreciate the opportunity.